Okay, we've got two cars. One moving at a constant 19 meters per second. Second car passes it, or it passes the second car moving on the same road in the same line, moving at 16 meters per second, and accelerates at 3 meters per second squared. We ask, when does it catch up? What's the maximum distance between the two? And what's the speed of car 2 at each event? By meaning when it catches up and when it reaches maximum distance. Well, if you think about it, the numbers match up real nicely. In 1 second, this car is going to speed up by 3 meters per second, so it's going to match the speed of car 1. Now, I didn't ask when that happens, but when this car matches the speed of this car, well, until it matches the speed, it's falling behind. But when it matches the speed, it's going to be moving at the same speed, and it's going to start catching up because it keeps speeding up. So at 1 second, when this car matches the speed of this car, it's going to reach the maximum distance between. So the answer to this question requires only just a simple little mental calculation of when the speeds match, if you understand that maximum distance occurs at the instant the two speeds match. Now, if you don't, it comes out of the equations, and that's good too, but it's kind of an important insight about maximum distance and slopes of, well, if you got the graphs of the two, at the point where the slopes are equal is the point where you reach the maximum distance, and you can do a lot with that too. I'm not going to get into that, but here we have it now. How do we set this problem up? Well, it's pretty straightforward to set up. You have to have an x-axis because you're going to be moving along an axis. Of course, you want to call it a y-axis or a q-axis or anything. You're welcome to do so, but we usually use x for motion in one dimension. So along the x-axis, the cars pass at some point. And we might as well call that point x0, so that implicitly when they pass, that's when time is equal to 0. And let x0 equal 0. I mean, we can put our x-axis anywhere we want. We can put 0 any place we want. That's a convenient place to put 0. Motion of the first car, then, you just write the kinematic equation for uniformly accelerated motion. The first car has x0 equal to 0. And of course I'm going to call the position of the first car x1, and I'm going to subscript the variables x0, v0, and a as x01, v01, and a1. Okay, so x01 is going to equal x02. Both of them are going to be here at t equals 0. v01 is the speed of the car at that time, and that's 19 meters per second. And of course, that's constant, which means that there's 0 acceleration. So the equation for the first car is just what you see here. This term becomes 0. You just have 19 meters per second times t. Second car, x02, well, they both pass at this point that we declared to be the 0 point. So that's 0, so you're just going to get x2 here. v02 is your 16 meters per second. A2 is your 3 meters per second squared, and here's the equation for the second car. Now, how do we determine when the cars, again, are at the same position? In other words, when the second car passes the first, because it's obvious that if this goes on long enough, this car is going to achieve unlimited speeds as long as it continues accelerating at 3 meters per second squared. So it will eventually pass this car. That's going to occur when x2 equals x1. I left the subscript off there. Okay? So they catch up when x1 equals x2. So we set x1 equal to x2 and solve the equation. It's a very easy equation to solve. It's a quadratic equation, but since the cars started at the same point, the coordinate of that point is the same on both sides. The coordinate of that point 0 anyway, and it's going to disappear from the equation, we get a very easy quadratic equation to solve. Just factor out the t and use the product of zeros thing. And you're going to determine that t is going to be 2 seconds. I don't think I ever wrote that down. You have two solutions. T equals 0 and t equals 2 seconds. You can verify those solutions. You can use the quadratic formula in this. You can divide t out and get the 2 seconds, but if you divide t out, you're not allowed to divide by 0. So you've got to consider whether t equals 0 is a solution, and you see that it is for very obvious reasons. Okay, then the distance between the cars is x2 minus x1. That's going to be then, well, here's x2, well, you do x2 minus x1, this is what you get. To figure out when that distance maximizes, you just use a little calculus. Because there's symmetry arguments you can make with quadratics and so forth, it'll work, but you want to be able to use the calculus. So you just use the calculus procedure for maximizing. You find critical points, and then you do a first or second derivative test. I'm not going to do that for you. If you have to review the calculus, then you should do that. Look up critical points, look up first and second derivative tests. You did it when you took Calculus 1, and it's a straightforward procedure, okay? So, anyhow, if I take the derivative of this, the derivative is going to be, well, derivative of t squared is 2t, half of 2t is t, so you're going to end up with 3 meters per second squared times t, and the derivative of t is just 1, so you end up with minus 3 meters per second equals 1, and you solve that for t, and that's very easy to solve. You end up with t equals 1 second. That's your critical point. You do a first or second derivative test, and you determine that your critical point does give you a maximum, so you get the maximum distance. Of course, we figured that out just from, my first comments, maximum distance between when the two velocities match, and that happens at 1 second, and that's obvious. You're going to get to do this problem with different numbers, so you're going to see what happens when things aren't as obvious.